Hello, I'm here to present this fun project of mine, building a neural network from scratch for classification task. It was really fun. I learned a lot. I'll get into this architecture and how I build it one by one, and go through those steps. But first, I want to start with this disclaimer here because maybe there are some learners out there. We don't want to mislead anyone. So this is not a standard way to build a neural network, and using the libraries it's one-liner and probably faster and maybe even simpler. Not maybe, it is simpler. But I did this like this to gain a deeper understanding, and I did gain a deeper understanding. I sometimes use pen and paper, sometimes use Google, sometimes use those ChatGPT tools, and simply thought over it many times, and in 1 week I built this. It is fun, and right now I clearly can say that when using those libraries like scikit-learn or pytorch, I'll just have a lot more confidence because many things just click. And yeah, let me not talk too much and show. So the network is simple. I have only 3 layers, one, two, three. And in the input layer, I use two features. In the output layer, I predict two binary classes, binary classification this is. And in the hidden layer, I tried many different, and at the end, I'll show you the hyperparameter tuning to how I choose the count of hidden layers as well. So at the input layer, I have a linear function as expected z1, and then I use a ReLU in the hidden layer activation function, and then I use another linear function followed by softmax to get the probabilities, and then I use cross entropy to calculate a loss, and then that is just one forward prop, and then loss calculation, back propagation, updating parameters, and looping of this, and trains my model. And yeah, we'll see all of them in right now. Yeah, so this notebook has various stages. So the first step is data prep because I need a data to solve a problem. I just don't want to build something that doesn't do anything. So yeah, and then there is this section called neural network architecture. In this section, I build the functional components of the neural network, and then I build an object that contains all those functions, and we'll see them here as well. And in the building and evaluating the network, I build a network, I generate a classification report, and I show my evaluation and hyperparameter tuning process for you. So here I import the libraries. I use only NumPy from scratch. I don't use assembly or 0 and 1s, but NumPy is as much as it gets in terms of building it from scratch. And pandas and matplotlib, etc. for visualizations, and for evaluation I use scikit-learn because I really don't need it to do those from scratch. That's not in the scope of this. So first let me get this mouse out of the way. First I get my data. It is this wine quality data set in this Kaggle link that we can be found. Oh, let me actually run this entire notebook so we see the results as well. So that will be done very quick. So after importing the data, I'll look at a sample of the data. After looking at the sample, I check the informations. So because I just started to run again, it starts the kernel session like it should have been done in 10 times right now. But yeah, it's running right now. We'll see in very quick results. Yes. Okay, I looked at a sample. Okay, it shows one. It's okay. And then I look at the info of the fields. We have a lot of numeric fields here. But what I'm interested in is simply actually this quality, and because this is my target variable, and I want to choose some features to predict it, and that's it. Still, I look at some descriptive statistics. This data is quite clean. All they seem to be follow like normality overall. Some of them are skewed, maybe some outliers here and there, but I don't want to dive deeper in those because this is a very focused project, and if my chosen features need some diving, I'll do them, but they didn't because I'm trying to predict quality, and I'll build a simple neural network for it. I generated this correlation metrics and looked at the quality and the correlated features to it. So once I did that, I found these two. One is here and the other one is here, and those are alcohol and volatile acidity. Those, although these are not very strong correlations, they're significant correlations to my eyes compared to others, and like not too much to my eyes, significantly better than the others. But yeah, I chose those two features to target my quality predict. And then I plotted my targets, and then I noticed that it has very imbalanced distribution. So this is bad. These classes will create a problem, and especially like yeah, in my first run, I didn't do this, for example, and my model predicted everything as 8, overfitted, and it was not useful. So what I did is I grouped them into good quality and bad quality. What is above 5 and below 5. This equals sign, yeah. And then this is the distribution of new classes. 0 is bad, 1 is good quality. So after that, I scale my features because to help model learn better, not to overfit to one feature. And then I use a train test split to split them into my train and test sets. And I want how to encode my features to be able to use them more for like easy matrix operations, to be very straight to the point. And this is the main part of this notebook. So I told you about the data preparation and our problem, and here is the network I'm building, and later on we'll see how this model solved that problem. Yeah, so this is a simple neural network, as I told you. So I have input layer, output layer, and a hidden layer and output layer. In the input layer, I have 2 features. In the output layer as well, I have 2 features. In the hidden layer, 2 classes. In the hidden layer, I have many neurons. And in between, I have weights. Also, when it comes to like weights and biases, and also in these layers, I have activation functions that simply hold those values. And after that, I use a loss function to calculate the cost, and that will make up one forward propagation. So as I said, layers, 1 hidden, 1 input, 1 hidden, 1 output. Activation function in the first one is ReLU in the hidden layer, and the A2 and the output layer is a softmax because I want to generate probabilities to map to those classes. And this is the forward propagation. So from features to Z1 to like linear function, and then nonlinear activation function, another linear function in the output layer when we go through it, and then activation function is a softmax, and then loss function, categorical cross entropy, and then there is the backpropagation. Backpropagation calculates the assigns the amount of blame from the error to the weights and biases so we can update them. Yeah, so this is not an entire lecture on neural networks. For those, there are a lot of other videos out there as well. So I will not be explaining every single detail to keep this shorter, and maybe someday I can definitely do that as well. But yeah, let's stick to the point. From loss function J to I start taking derivatives and going back and found the gradients for weights 2 and bias 2 and weights 1 and bias 1, and then I used those gradients in the update parameters with the learning rate. And there's one epoch, as I mentioned again, forward prop, loss, back prop, update parameters, and then I predict with argmax, or like I use in a threshold, and there's the training process and the neural network object implementation. So in this section, I'll show some of the functional components like layer, activation functions, forward propagation, the loss function. But in the object implementation, I have put everything together for a cleaner code. So there it will be much cleaner to see. So first I've tested it one by one with smaller functions. I just built the input layer, hidden layer like this. I've just created simple matrices with NumPy, and then I created an activation function, for example. For the value, it just takes the maximum between if it's 0 or the number itself. For the derivatives, if it's below 0, the tangent is 0. If it's above 0, it is 1. It's simple as that. For the softmax, this is taking the exponential of the number and then dividing it to the exponential of everything. But just for this computational safety, there's this operation of subtracting it from the max. The outputs probabilities are the same, but yeah, it helps with the generate now computing over very large exponentials, because these things grow exponentially. Anyway, for the derivative, I didn't write a explicit function. I did it in the backpropagation implementation. Maybe, yeah, I'm sure it would be good to write in a new function like this, but because I use a chain rule there, some things get simpler, and it just would be over engineering for me to try to write a distinct function for this. So it works for my purposes, and I will use the standard libraries anyway, so it's okay. So I'll show that too. So in the forward propagation, it is simply taking one linear function, like weight 1 over multiplied with our features, and the biases are added, and then followed by ReLU. This gives us the A1 in the hidden layer. In the A1 to the output layer, there's another linear function. This time V2 multiplied with A1 and plus with the bias, and then the output non-linear function softmax to get the probabilities in the output layer. That's one forward propagation. And then there's this categorical cross entropy. Simply what we do is that we get the log of the probabilities, and then we calculate the element-wise costs. This simply enables to render or filter out those probabilities that correspond to the zeros in the one-hot encoded matrix, which is already featured, our true matrix. And then I take its mean, so it represents the same unit across different loss calculations. So basically we're taking the mean of it. So the back propagation, this is the very juicy part of this neural network. So after one forward propagation and calculating the loss, I go from loss to A2 to Z2 to weights and biases of 2, I mean the gradients of them, and the same goes here to A1, Z1, and the weights of biases of the first linear function, and I use those in my update parameters function. So let me try to show you this very quick. If you are into it, how I did it, these notes are good, and I have this scratch notes here and many things on my notebooks as well, I mean in pen and paper, but it's simple actually. There's just one chain rule here. For example, once I have the cost J, so derivative of J in respect to A2, and because I'm trying to go to the linear function Z2, and then another derivative from Z2, I mean derivative of A2 with respect to Z2. So the chain rule cancels these two and gives me directly to the derivatives for the DZ2. So, and then I calculate them to like divide them into the weights and biases. So activation function 2 here corresponds to the softmax, and J is the cross entropy loss function, and this is the linear function. The cross entropy, it has a simple derivative. So in terms of units, it's simply just a logarithmic log of one probability, and the cost of it is 1 divided by that probability, I mean derivative of it. Because it's a cost, it's a negative, and because it's not unit, it's everything. Minus y divided by all probability matrices. So the scalar notation is this, and the vector notation is this. For the softmax, there is more nuance to it, because softmax gives us probabilities, and the magnitude of one increasing it and decreasing it affects the other classes. So we had to look at self-derivative and other derivative. When I run the math, and it's not too hard, some notes are here as I said, and you can do it. Maybe I don't even need to go into details of it here, but simply for the true class I get this, and for the others I get the minus AI and AJ. So what happens good, interesting about this is that, when we consider correct classes and the wrong classes and multiplying with like applying the chain rule like this, we multiply slope of the loss and the slope of the softmax for the correct classes and the wrong classes. So we do this twice, and turns out there's one good representation that shows the covers the output of the both scenarios. So one scenario is AI minus 1 when we multiply these together, because these remove each other. AI minus 1 for the true classes, AJ minus 0 for the wrong classes. So AI is, so when we predict 1, and AJ for the wrong classes when we predict 0. So it turns out these are the same thing. So applied to the matrix, it's simply all the predictions we have and all the true values in the Y matrix, and this turns out to be a pretty good representation of these both scenarios. And simply entire calculation and notes here adds up to this one line, which is A minus Y, and it is beautiful. Anyway, from there things get easier, because now because the softmax derivative is the most problematic thing was here. Oops. So after we have the dz2, what we needed to do is divide it to these weights and bias. So we take three derivatives here. The first derivative is to find the gradient for the v2. When we take a derivative with respect to this removes and we only get a1. So what I do is we take a dot product of dz2 with a1 here. So that gives us the gradient of dv2. And for the bias 2, it just removes this section entirely and we just get 1. This is a simple derivative operation. And then to go back in the layers from z2 to z1, I take a derivative respect to a1 and then we get rid of these biases removed, and yeah, we simply, yeah, it is v2 with the dz2. And then once I have the dz1 da1 activation, I'm at the, so I came back to the hidden layer right now. So we started from here, from the loss function, we calculated the weights around here and the biases, and we came to the A1 layer. So the final thing is to calculate the weights and biases here. So calculate them, we just do the same thing over here, but with the things respect to in this layer. But yeah, to get back to the dz1, to overall error here, I needed to take the derivative of ReLU as well. So from da1 to dz1, I used the derivative of ReLU. Sorry for the bad notation here, but I hope it's clear. So the same thing, taking the derivatives with respect to weight 1 and the bias 1, and taking the dot products, and we get to these gradients and return them and use them in our update parameters function here. And in update weight parameters, I just use the current weights and subtract the gradients from the current weights and assign it back. But before subtracting the gradients directly, I multiply them with the learning rate to adjust our step sizes. So yeah, that is mainly the thing that summarizes the entire network. Yeah, let me show the rest. So this part I'll kind of skip very fast because the object is clearer. I defined an epoch function for my test, and it helped me in the prediction and training. But simply, this is my neural network. The rest is me building it and explaining it to you. And this one doesn't have that much nodes. It's a lot cleaner and ready to go. I can just instantiate these objects and I can use it, and it's very similar how I guess a regular neural network, to be honest. And to initialize it, I need to give it to input, hidden output, and this seed is to make sure I get the same numbers each time so I can test it. And yeah, I need to give it to inputs and hidden and the output layer sizes. Activation functions, same as above, and the network operation, the same as above. Forward propagation, calculating the cross entropy, and then the backward propagation. This is the same thing above as well, but this doesn't have those huge comment lines. It is a lot cleaner. It's just very to the point. So if you just want to do it, it's just this, for example. Or if you just want to use build a neural network with a scikit-learn library, it's just a one-liner actually. But the point is not to write this. The point is to understand how that backpropagation actually happens and how those things works. And yeah, it helped me a lot, to be honest. So I did these and calculate the gradients. Same thing as above. I update the parameters like this. I have a training function. I give it to my data and then define, like give it an epoch count, how many times this loop will run, and the learning rate to adjust. So the one forward propagation followed by a loss, and then backward propagation followed by update parameters. And I take a note of this loss numbers. So, and then I plot them and use them. There's this prediction function which predicts in two different scenarios. If I don't give it a threshold, it uses an argmax to assign the class with the highest probability. If not, it uses a threshold. It's simple. And the predict prob uses the same self-propagation function to get to the probabilities, but it doesn't generate predictions, returns the probabilities directly. Yeah, so that is the entire network. And here, how I instantiated. So this is like this very same thing with those libraries when we build these models. So when I wrote these, it's a lot of things kind of clicked. So here I instantiate my object, give it the size of it, and then I train it with my input, output, and then epoch size and the learning rate. And here is how I predict and get the predictions, probabilities, and one classification report to have a look. So this is the model I choose to build after evaluating and tuning its parameters. I'll show you how I did those after this part. But yeah, this is the final model I built, and it's quite good. As you can see, consistent numbers, and yeah, across different categories as well, and quite a good ratio. It's a good model. It can be, yeah, this is not the point is I'm curious how this model would work actually on a data that it didn't see, so I might even try that as well, but I might solve more complex problems after this, so, or like business problems. Yeah, I'll see how it goes. So yeah, overall though, I like these numbers, definitely. So experiments to fine-tune the hyperparameters. I looked at what threshold to use because I like that idea of using a threshold instead of getting the 0.5 directly. So I have this rock curve, and the area under the curve is quite good. I like this. Of course, like it would be nice to have this, but that thing doesn't exist, as we know. So this gave me a good idea. I would like to have some thresholds over here, so that's good. And what I did is that I also look at the true positive rates across different thresholds. So actually these 0.5 turn out to be quite at the same range of this area that I chose as a good area for my potential case. Of course, this depends on business cases. Maybe we care more about this, so it could be good to choose some things over here. So but I wanted to care about my true positive rate more in this one. Yeah, and I need to choose something, and I like its statistical consistency was one of the concerns as well. So 0.5 threshold in a binary classification is kind of makes sense. And choosing the learning rates, I tested with a lot of different learning rates. This is an interesting part, because when I plotted this different models with the different learning rates, of course this can be done in many different ways that we're just scratching the surface over here. But yeah, this is the one visual I have. And in this one, so I plotted the learning rates from small as this to big as 3. So usually this is what we see in the real learnings, but I decided to go with an aggressive learning rate, which is 2, and the reason is that the plot is quite good, and in my test it turned out to be good. Maybe my data doesn't require like the heel is smooth is the term. My data doesn't have that much complex patterns maybe, but still if we take a look at this learning rate tree, there's this huge spike. So this is model taking very big steps across different hills and taking wrong turns and not finding the local minimum. But yeah, maybe it would happen on a data that it didn't see on my on my learning rate as well. But I think for now it's good. So in a hidden layer size, I looked at different hidden layers. So here I have a similar plotting. So I looked at some hidden layer sizes like 500,000 or 2,000, etc. But my data points doesn't have that much data points. So I wanted to go with something smaller in this range. I tried things in the smaller area like 1 to 10, but those were not so useful, not so great, although they were somewhat useful. I tested this area and choose 90. Because I choose 90 is everything kind of follows linear performance increase here as the complexity increases. Like the hidden layer size increases, the model learns the patterns in these dataset very well, but maybe the risk is that if you go over here, it will be over parameterization, like the memorization instead of learning. But the 90 did something interesting and jumped over the 100, and because of this, I wanted to choose 90. Yeah, he has hidden layer size because it has the most effective gradient descent size. Yeah. Based on these is the model I have as the results. And this is the object, and it's how it created. And maybe I talk too much, but the project and going over it required me to do, and I wanted to do because I really loved working on this project. I hope it showed some things, or I hope maybe if you're here to learn, if it helped in some sense. In the future, I plan to build educational contents on these areas. Those would be more focused on teaching instead of showcasing how a thing is built. So, but yeah, time will show. Thanks for watching. Wish you all a beautiful day. Yeah, it was a fun project.